All right, hello everyone. So this week we're going to be doing chapter 8, which is all about alkenes. We've talked a little bit about alkenes up until this point. In particular, they were the products of our elimination reactions. But this chapter we'll be talking about what types of reactions alkenes themselves undergo, and we'll see these are all addition reactions. But before we dive into the actual reactions, let's take a step back. We got to figure out how to name our alkenes, right? So some alkene nomenclature. So the rules that you're going to go through are fairly similar to when we've been naming our alkanes or our alkyl halides, but there are a few distinct differences. Those are going to be what's highlighted in blue here. So let's just take each of these point by point and go through some examples. So first of all, our ending has changed, right? So for alkanes, we had this ANE ending. So for example, pentane. For alkenes, they have the ene ending, ENE, okay? So this, so that would be pentene versus pentane, okay? I think one of the biggest changes is going to be how we number our parent chains. We're always going to number our parent chains such that the parent includes the double bond. So for example, when we had our alkane 1, 2, 3, 4, 5, 6, 7, 8, and actually the numbering would be the reverse direction because of that substituent there. 4, 5, 6, 7, 8. So this was the longest chain within this compound. So that's why we said that this was the parent chain. So it was an octane. Notice here we still have that 1, 2, 3, 4, 5, 6, 7, 8. Our longest chain of contiguous carbons is still 8 carbons long, but numbering the parent chain this way would not include the double bond in the parent chain. So this is not the correct way to number. We're always going to number such that that double bond is included in our parent chain. Okay, so over here, this was an octane, but this would be a heptene, because again, we're going to number it such that the double bond is in there. Not only that, but we're going to number it such that the double bond always has the lowest possible numbering scheme. Okay, so just like before, once you identify your parent chains, you can either number left to right or right to left, right? And there was this consideration of, oh, we want to make sure that our substituents have the lowest possible number. Well, when it comes to alkenes, the double bond wins. We always make sure that the double bond has the lowest number. So this would be the correct way to number it. And we locate the position of that double bond based on whichever the smaller number is. So we would say that this double bond is located at carbon 2, which really means it's between carbon 2 and 3. But notice this would be the correct numbering scheme. We would not number it the opposite way. And this would be true even if, let's do another example that's kind of closely related. Okay, this would be true even if we had another carbon over here. All right, so again, we have two different ways of numbering. 1, 2, 3, 4, 5, 6, 7, 8. Or 1, 2, 3, 4, 5, 6, 7, 8. Okay. Notice on the left-hand side, my double bond is located at position 3. On the right-hand side, I have a methyl group located at position 2. So previously we were doing whichever was the lowest number, that was the correct numbering of the parent chain. When it comes to alkenes, we're really focusing first on that double bond when we're numbering, and it's all about giving the lowest number to that double bond. So this is still correct. Even though this is a 3 versus a 2, this is still the correct way to number because it gives our double bond the lowest possible number. Okay. And then how do you include that position of the double bond in the name? So we got to include it in the name, just like we include the position of methyl groups and ethyl groups and all that good stuff. Again, it's whichever the lowest number is, that's how this is going to get into our name. So this would be the, in this case, you have 5,5,6 trimethyl 2-heptene. Okay, so that 2 out front is indicating the position of that double bond. An equivalent way to do this, it's also perfectly acceptable, is to say het2-ene, all right, where you put the 2 just in front of that ene suffix. This kind of looks a little weird. It will make more sense as to why that's an acceptable numbering scheme when we have multiple suffixes. So for example, if there was an alcohol in here as well, we would have to include it this way. For now, this is kind of the more, it's not, again, neither of them are incorrect, but this way is sort of the more correct looking or a little bit less funky of a way to do it, where the number out front indicates the position of that double bond. So if we were going back, for example, to our original pentene, 1, 2, 3, 4, 5, the correct name for this compound here would actually be 1-pentene. And again, that 1 is indicating the position of that double bond. The last thing that we're going to have to worry about is stereochemistry. Remember when we were talking about alkenes, they have this EZ stereochemistry. You can use cis and trans sometimes. Remember, there has to be a hydrogen on both sides of the double bond. So if instead of a fluorine over here, this was a hydrogen, then we could refer to this as trans. But sort of the foolproof way to go is to always use the EZ nomenclature. You can use that to talk about cis and trans compounds where you can't use cis and trans to talk about all alkenes. Remember, what we do for these is we chop the double bond in half, and then we're going to assign high and low priorities on either side. This is the same way that we assign priorities like we do with our RS stereochemistry. First consideration is atomic number, and then from there on, it's who's bonded to who. So in this case, here would be my high priority group, here would be my low priority group, high and low. And since the high priority groups are on Z-same side, this would be a Z stereoisomer. Okay, so yeah, so for here would be my Z stereoisomer. If those 2 high priority groups, again, chop at the double bond, high, low, high, low. If they were on opposite sides, that would be the E isomer. Okay, but just like we included R and S into our nomenclature for the alkyl halides and the alkanes, we're going to have to include our stereochemistry in our nomenclature for alkenes as well. Last sort of like qualitative stuff that we kind of went over but last chapter, but just to reiterate, the cis isomer is generally less stable than the trans isomer because of the steric strain that occurs from having 2 big bulky groups on either side. And it's not even as easy as saying always cis or versus trans or always E versus Z. You really have to look at your double bond. And again, you want to make sure that those big bulky groups are on either side. So even though, well, I guess if we just did something like this, this would be the Z isomer, which would be less stable because you have these big bulky groups that are clashing, right? So the name of the game is for alkenes in terms of evaluating stability, the bigger the group, the more that they want to be on opposite sides of that double bond. And what do I mean by more stable? Well, we can actually measure this using like heats of hydrogenation, right? So if we take, for example, this would be the trans, and this would be the cis stereoisomer. Another way to say that would be the E or the Z stereoisomer. And we do a combustion reaction where we react this with oxygen. Both of these will produce the same amount of carbon dioxide and the same amount of water. But one of them actually releases more energy than the other one. Okay, so what does that mean? Well, if we think about this in terms of our enthalpy tables, if it's releasing more, or I'm sorry, enthalpy diagrams, if it's releasing more energy, more heat upon this reaction with oxygen, what that means is that it started out at a higher energy and was thus less stable. Right? This would be starting out at a lower energy, so it is more stable. So you can actually measure these things. And in this particular case, you'd see that the difference between them is about 4 kilojoules per mole. And that's only going to get more, that difference is only going to increase the more bulky those groups are. So if these were, instead of just being methyl groups, were tert-butyl groups, for example, we'd expect that gap to be that much more significant. And the last thing we also talked about last class, but just to keep in mind, last week, but just something to keep in mind, the more highly substituted the alkene is, the more stable that alkene is, right? So that means, by that I'm looking at these allylic positions, and the more carbons I have in the allylic positions, the better. All right, more alkyl groups means more stable. More highly substituted alkenes are more stable. All right, and then the last thing to talk about would be what happens when we have cyclic alkenes. Well, for most of our cyclic alkenes, for rings that have 7 carbons or fewer, you can only have a cis alkene, right? There's no way to have a cyclohexene that's a trans cyclohexene, for example, because these bonds are kind of locked on that same side by that ring. If you do have larger rings, 8 or more carbons, it is possible, but that's not something that I'm honestly going to worry about too much. You can figure out whether one's stable or not using this Brett's rule. I'm not going to bother with it. It's not all that big of a deal. We're going to focus on carbons, rather cycloalkenes that have 7 or less. So they're always going to have this cis stereochemistry. And because of that, you don't have to include the stereochemistry in the name because it's kind of implied. Okay.